In this lesson, we're going to look at applications of set theory. We have two triple venns, and then we have one set question that we'll look at the end, which is very similar to if anyone's played the card game set. Has to do with that. So let's take a look at the first example. It says, use the following clues to answer the questions below. Now in the past I've sometimes done example 2 before doing example 1. So if you've gone through this one with me and you're a little bit confused, try looking at the second example and then coming back to this one. Okay? So we've got a list of information here that we're going to have to sift through and figure out what to do with. We've got 28 children have a dog, a cat, or a bird. 13 children have a dog. 13 children have a cat. 13 children have a bird. So I'm going to define my variables right away because I can see that we're going to have to deal with dogs, cats, and birds. So let's define those right away. Now 13 plus 13 plus 13, that's giving us 39 total here. Although it says we've got 28 children have a dog, a cat, or a bird, we've got 39 total when we add those up. Now 4 children have a dog a dog and a cat. 3 children have only a dog and a bird. 2 children have only a cat and a bird. So if I actually go back here for a moment, what they're telling me up here is the number of elements in D is 13. The number of elements in C is 13. The number of elements in B is 13 to give us a total of 39. Where down here, 4 children have only a dog and a cat. The number in D intersection C is 4. The number in D intersection B is 3. And the number in C intersection B is 2. Okay? No child has 2 of each pet. Well, this has no effect on what we're doing. Okay? Now, if we look down here, they've set up our triple venn already. So we got to figure out where all of this information is going to go that they're giving us. It says how many children have a cat, a dog, and a bird? How many children have only one pet? So bird only, cat only, dog only. Now up here I was saying that 28 children have a dog, a cat, or a bird, although we've got 39 here. And that does not equal to 28, right? So we've got 28 children, but 39 total. So if I'm going to define my variables on my Venn diagram, so I'll put that one for birds, that one for cats, and down here we'll use this one for dogs. Okay? They're saying that each of these is 13. But that includes the overlaps, right? So we've got an overlap here. We've got an overlap here. And finally, we've got an overlap here. And you'll notice in the middle part, that's 3 overlaps, right? We've got 3 overlapping layers going on there. So when we're saying that 39 does not equal to 28, that's because there are regions that overlap. I'm using B/C for because. Okay? Now, in this section here, we have 2 layers because we overlap twice. But we just need to subtract that off once. And I'll explain further what I mean in a moment. So that's going to be the same for all of those sections, right? This is 2 layers. And this is also 2 layers. Okay, so subtract once. Whereas in the middle part, right, we've got 3 layers here. Which we've got 3 overlaps. So we're going to have to subtract out twice. So what I'm talking about here is I just want to be left with 1 layer in each spot. So if I have 2 layers and I remove 1, I'm left with 1 value there. If I have 3 layers, I have to take 2 layers off, so I'm just left with 1. Because in A, what they're asking us to do here is find how many children have a cat, a dog, and a bird. That's my middle section. So if I get rid of some of this, this is my X. This is what I'm trying to solve for, right? I don't know what that value is. So I know that we've got a total of 39 when I add them all together, 13 plus 13 plus 13, right? And I'm going to subtract off all the regions that overlap more than once. When I subtract that off, I should be left with that 28 value that we've got up here. Okay? So I want to know what that true value of X is. I don't want to have it double, triple counted. Take that away. So 39, subtract everything else. Well, what is everything else? We've got all of our values listed there, but we haven't put them in our Venn diagram. So let's do that. Get rid of these arrows here. You can put them back, just I was maybe a little bit too excited when I was drawing those in there and they're going to get in our way. Okay, so what are our values that have to go in there? The 13s I already have in there, and now it says that 4 children have only a dog and a cat. Okay, so that 4, where does that go? That's right here. Okay, that means I'm only interested in this section here, not the part in the middle. Three is the intersection of D and B only. Okay, and 2 is the intersection of C and B only. Okay, so we know that that middle part isn't included there. Figure out X. How do we figure out X? Well, 39 minus the regions that overlap more than one. So I have 39, subtract off the 2 once, subtract off the 3 once, subtract off the 4 once, but because that X there is overlapped 3 times, we have to subtract it off twice. And then we'll get that 28 value. Okay, we're going to do some algebra here and consolidate this. So 39 minus 2 minus 3 minus 4, that would give me 30. Combine the 2 x's, that would be minus 2x. is equal to 28. And we're solving for x. We're going to get that middle number. And once we get that, then we can get these values as well. Okay? So get rid of the 30 by subtracting it from both sides. And I end up with negative 2x is equal to negative 2. I like that because when I divide both sides by negative 2, I end up with x is equal to a positive 1. What does that mean? I'm going to get rid of this here. That means that only one child has all 3 pets. And if we want to write that out using set notation, the number of elements in B intersection C intersection D is equal to 1. So we can write that up here. How many children have a cat, a dog, and a bird? The answer to that is 1. Now B is asking us how many children have only one pet. So for B, the number of only cats, the number of only dogs, and the number of only birds. Well, now all we have to do is subtract. So if we look at only cats, which is the value here, we're taking the 13, which is all of this, right? And subtracting off the 2, the 1, and the 4 to get what's left over. So 13 subtract 2, subtract 1, subtract 4, which gives us 6. And the same thing for dogs and birds. So if I look at the dogs here, all of this is 13. Subtract off the 3, the 1, and the 4 to give me 5. And finally, for the birds, 13 subtract 2, subtract 1, subtract 3 to give us 7. Now, what exactly is that B asking? How many children have only one pet? We're not just stating those separately, but they're asking for the total here. So sum those up. 6 plus 5 plus 7 to give us a total of 18 children having only one pet. Okay? So just be aware, even though you're solving all this information, you got to go back and see what exactly they're asking us to solve. And you can put those values in your Venn diagram so it's more complete. There you go. Let's have a look at example 2. Shannon's high school starts a campaign to encourage students to use green transportation for traveling to and from school. At the end of the first semester, Shannon's class surveys the 750 students in the school to see if the campaign is working. They obtain these results. You can see them all listed, and then it says how many students use green transportation for traveling to and from school. And it shows us that somebody else solved the problem. We're not going to do this and determine the correct solution. So let's just solve it the whole way through. So let's just, eliminate this and just solve. Okay, so going back here, they give us a list of information, but we don't necessarily have to use it in the order that they gave it to us. What do I mean? Well, first of all, let's define our variables. We've got students who take public transit, students who cycle and use public transit, students who walk and use public transit. So I can see here that my 3 variables, or my 3 sets, are going to be T, transit, W, walk, and C, cycle. Okay, so students who use public transit, down here I've got T, W, and C, just to putting my variables, labeling them on here. We've got 750 students total, so that's my universal set. And now I want to figure out how many students use green transportation for traveling to and from school. So in order to do this, let's fill out our Venn diagram and figure out what information we have here. 370 students use public transit. 100 students cycle and use public transit. 80 students walk and use public transit. 35 students walk and cycle. 20 students walk, cycle, and use public transit. 445 students cycle or use public transit. 265 students walk or cycle. Looking at this information, where is a good place to start? Now, if you said here, I agree. Why? Well, 20 students walk, cycle, and use public transit. That's all three. Let's put that on the diagram first. Where would that go? Well, all three, that would be the middle here, that overlapping. So that's where that 20 is. Once I have that, it says 35 students walk and cycle. So where is that walk and cycle? That would be here. Okay, so if 35 students, I'm looking at the second one here, 35 students walk and cycle, then how many students would just be in this section? Well, that would be 35 minus 20. And that would give me 15. And I could put that value in here. So what I'm doing is it's like a puzzle that I'm trying to undo and unfold so I can get all the pieces. Once I have all the pieces, then whatever they ask me, I can solve then. So let's go to the next one here. 80 students walk and use public transit. So that would be this here. So if I want to uncover that, if I take the 80 minus 20, I would have 60 use transit or walk only. Okay. Moving my way up, 100 students cycle and use public transit. Same idea. So that would be referring to that information. So if I take 100 minus 20, that would give me 80 in this spot here. Okay. 370 students use public transit. Well, how am I going to use that information now? Well, how is that useful? Well, if I take that 370, subtract off the 60, subtract off the 80, and subtract off the 20, I'll be left with 210 students who use transit only. Why did I do that? Okay, so they're saying 370. If I put that value out here, 370, that's all of this. Use public transit. Well, I don't want all of that, right? I just want what's in this only. So I'm taking that 370, subtract off the 60, subtract off the 20, subtract off the 80, and I'll be left with the value that we're looking for. And we got 210 there. Okay. Down here, 445 students cycle or use public transit. Well, that's different. Now I'm seeing an or there. Okay. How do we deal with the or? 445 students cycle or use public transit. So that would be all of this and all of this. Right? That would be all of that together. So to solve for the piece that we're looking for, which is just this, I'll take that total, 445, and subtract all the other pieces off. So 445, subtract 210, subtract 60, subtract 20, subtract 80, subtract 15, gives me 60. 60 students who cycle only. So just because there's a piece of information here, 445 students cycle or use public transit, I'm using that 445, but not necessarily to find anything about what they're talking about. I'm using it to find other pieces. I'm deducing from the question what I need. The last piece of information is going to help me get the walk only. 265 students walk or cycle. Walk or cycle, same idea. That would be all of this. So if I take the 265, subtract everything in those two circles, I'll get what I need. So 265 minus 60 minus 20 minus 80 minus 15 and minus the other 60 would give us an answer of 30. Okay? Venn diagram is complete. But what are they asking us to solve for? How many students use green transportation for traveling to and from school? So I'm going to write this at the bottom just so I have space. So the number of students who use green transportation is going to be the number of students who walk or cycle or take transit. And if we remember, when we use the union, that means to add. So that'll be the number of students. If that's or, that would be everything shaded. It would look like this visually. And we would be adding all of those numbers together to get the total. Okay, so that would be 210 plus 60 plus 30 plus 80 plus 20 plus 15 plus 60. Make sure you're keeping track of all those numbers, and you would get a total of 475 students. Good idea to go back and have a look at what we did step by step. It might be overwhelming at first to see, okay, where do I start? How do I know where to start? But the key for most of these Venn diagrams is that middle number and then working your way out. Is that going to be the case all the time? No. The nice thing about applied, you may argue whether it's nice or not, is that they can start these questions at any point, giving you different pieces of information, and you need to be able to attack that question from whatever angle they give it to you. Okay? So have a read through it again, make sure you understand, and we'll go over some more of this in class tomorrow. Don't forget to ask questions. That's going to be the key. Okay? Let's take a look at the next page here. This question is very different than the questions we were just doing, but it's still set theory. Example 3. If anyone has ever played the game Set, the card game Set, this is along the same lines. You can see in my notes package here, I've got color. You may want to use color for yourself as well. Okay? So you're given these 9 cards, and from these 9 cards have different attributes. Okay? We've got color, so you can see 3 different colors, blue, green, red. We've got shapes. We've got triangles, squares, and circles, and then we've also got the number of shapes per card. Some have 1, some have 2, some have 3. Okay, so it says Star is playing a game that involves sets. She's using the 9 cards shown, which have 3 different attributes: shape, color, and number of shapes. There are 3 shapes, triangle, square, and circle, 3 colors, red, blue, and green, 3 numbers of shapes, 1, 2, and 3. I just went through that. To win, Star must create 4 sets using 3 cards in each set from the 9 cards shown. Each card may be used in more than one set. So you make your set and then you return the cards, and then you look at the 9 again, you make another unique set and then return the cards. So you can use the cards over and over again. What we're being asked to do is find how many sets can be made. So find the total number of sets. What sets can Star make to win the game? So rules for creating sets. Sets of 3 cards must agree with each other or disagree with each other with respect to each attribute. 3 cards form a set if the cards display the same number of figures or each displays a different number of figures, and the figures are all the same shape or 3 different shapes, and the figures are the same color or 3 different colors. So the first one here is a set because we've got 2, 2, and 2, so that agrees. We've got blue, blue, and blue. That agrees. And what disagrees is we've got triangle, square, circle. So that's considered one set. We've talked about all 3 attributes, and either all the attributes agree or all the attributes disagree. For set number 2, we've got blue, green, red, so color disagrees. We've got 1, 2, 3, 1, 3, 2 if you're reading it in the order. So the number disagrees. And the shape also disagrees. Square, triangle, circle. Take a look at the last one. Why is this not a set? Well, I've got 3 different colors. Red, green, blue. That seems fine. Those all disagree. I've got 1, 2, and 3. Those all disagree. But we've got 2 triangles and 1 circle. So this last card should have triangles in order for it to be considered a set. But because we don't have any cards that have 3 blue triangles, we can't make a set out of that. So you can sit here and sort through them and pick them out, and that's one way of solving it. Or we can create what we call a tree diagram. And a tree diagram is a way of organizing your sample space or the list of all the possible outcomes, so that then once you have all the possible outcomes, you can decide if they're a set or not. So the way you want to organize your page, we're going to be working across. You need to have enough space, and sometimes the first couple times you draw a tree diagram, you don't necessarily have enough space. So the way a tree diagram works is you branch off of each attribute in this case. So the first attribute we can talk about is color. So the colors will either, I'm going to just scroll this up so we can see, we can either have cards with the same color or cards with different colors. Okay? Now, if the cards are the same color, like we have in this first set, they're all the same color. If we look at the next attribute, which is shape, in this case, all of our shapes disagree, or all of the shapes can agree, right? So if it's the same color, and branch off there, there's 2 options. We can have the same shape, or we can have different shapes. Now the same holds true for different color. If all 3 cards are different colors, which is fine, that means that they all disagree, then we can either have all the same shape or different shape. Now, if we have the same color, the same shape, the last attribute is the number. Same number on each or different number. And that would be true for all of these, okay? Now all we have to do is compare what we have here with our cards and see if that holds true. Okay? How do you read this tree diagram? And get a color here. So I would go same color, same shape, same number. That would be one set. So do we have cards to create same color, same shape, same number? Have a look up here. We have cards that are the same color, yes. Do we have cards that are the same shape? If we choose any 3 cards that are the same color, same shape, and same number. So that's not going to be true. It's impossible to create a set, right, of all red circles that are the same color, or so the same number, because I only have 2 things that are red and they're different. For green, I have 2 cards that are green that are the same color and the same shape, but not the same number, and I only have 2 of them. And for the blue, same color, I have none that are all the same shape, even though I have some that are the same number. So in this case, it is, for the first one, not possible. Let's take a look at 2. And what you're going to do is you're going to evaluate each and every one of these to figure out which cards we have in order to make these sets. Okay, and you'll see that for 2, that one's actually not possible as well. So that would be same color, same shape, different number, and as you saw before, so blues and greens are out right away because I don't have 3 cards that are the same color of red and green. Did I say blue? Red and green. If I look at blues, different number. Okay, so I have 2 blue circles and 3 blue circles, so they're the same shape, but I don't have any 1 circle. Same with the green card, the squares. I have 1 blue square, 2 blue squares. I would need 3 blue squares in order to create that set. So that one's not possible as well. All right, let's take a look at 3. I'm going to do the first 3, and then I'm going to leave you to do the last ones. If you want to check with the notes and see what other sets I created from here, you can go ahead and do that, and we can talk about it in class as well. Okay, so let's look at this last one here. The last one I'm doing, but you can finish the rest of them. So if we have same color, different shapes, same number, what possibilities do we have there? Okay, same color, so they're going to have to be the blue ones because I only have 2 red, 2 green. Different shapes, that's fine. I've got blue triangles, blue squares, and blue circles. But they're the same number. So that's actually the set that's sitting right here. So I've got 2, 2, and 2. Same number. Different shapes, triangles, squares, circles. Same colors, blue, blue, and blue. So we can actually draw that out. I've got blue, triangles, that's 1. 2 blue squares, that's the other one. And then 2 blue circles, that's the other one. So this is a possibility. That's one of the sets she could create from there. Okay, I'll do one more. I said I was only going to do one more, but I'll do another one just so you get the hang of it. Because the first 2 weren't actually sets. And could you create 2 from the same one? Of course you can, right? Like if there was another way of having the same number, the same color, and different shape, you could have 2 branching off that same one. So here we have same color, different shapes, different number. How can we get that one? Same color, so I guess that's our blue again, right? Because that's our only possibility. Different shapes, but different numbers. So I've got 1 blue square, 2 blue triangles, and 3 blue circles. Same color, different shapes, different number. And then my circles. So these would be playing cards, like a deck of cards, and you can sort through them like that. Okay, so I've done the whole tree diagram for the first 4 possibilities. I'd like you to go through under different color, try all the different possibilities, and see how many you can get from there. And we'll go over the answers in class. Thanks for joining me today.